Like, here's the ring and sum, find the original.
Okay, so last day, last class, yay, or last class for me, I don't know about for all of you. So kind of congratulations for hanging in there. Back on our very first class, I kind of challenged people to keep a physics streak. And I said if you did some physics every single day from day one to today, you would get a prize. So if you've kept your physics streak, please let me know and I will get you a prize. And it has to be every day. You can't have skipped, not even once. So anybody who did it every single day has earned a prize, which I will get to you as long as you let me know. So today we're going to finish up. Are there any questions before we get started? So we're going to finish up what we started last day. We talked about Faraday's law, which was induced potential, and Lenz's law, which let us figure out some of the directions of all that stuff. So last class we were mid-example when we had to quit. So why don't we pick up with this example right here. We have a current in this long straight wire. And that current is decreasing. Okay, so there's lots to this question. What current gets induced in this little square loop? So why don't we go through this step by step. This is a current carrying wire, so this makes a magnetic field. What's the direction of the magnetic field over here made by this wire? So the one person I saw going with the right hand was doing it. So your thumb goes with your current. What are your fingers doing at the page? They're going into the page. So the magnetic field is big circles right here at this point. The field is into the page. If the loop was over on this side, the field would be out of the page, but it's not on that side, it's on this side. So B is into the page. If the current is decreasing, what does that mean about the magnetic field? Decreasing, right? So B is mu naught I over 2 pi r. So B is into the page and decreasing. So what is the direction of the induced magnetic field going to be? It's got to oppose the change.
Going out of the page.
Okay, so the first answer was out of the page. Who agrees with out of the page? Lots agree. Does anybody disagree? Okay, one lone voice. Let's hear your argument for disagree.
Okay, so we start with B going into the page. Now, if it's decreasing, I'm imagining the opposite direction, so it would be coming out of the page. But now we need to do the opposite of that. So
Yeah.
that means that our induced is going to be into the page.
Okay, is anybody now going to change their answer? Yes, got some answer changes. Okay, so it's into the page and it's getting smaller. So let's say it's going from 10 Teslas down to 5 Teslas. Nature does not like that change in magnetic field. It wants it to stay at 10 Teslas into the page. The way to make it stay big into the page is to create a new field which points into the page. So we're always opposing the change. So because it's into the page and decreasing, the induced field is into the page.
So it would be going out of the page if it was increasing.
Yes, exactly. So there's our induced field, is into the, into the page. Been a long term for me too. Okay, so let's think about what does this mean about the direction of the current. So what we can do is let's look at this bottom loop right here. Let's think about the fact that the magnetic field is into the page right above the loop. So my thumb is going to be with the loop and my fingers are the magnetic field. My fingers are going with the magnetic field pointing into the page and my thumb points this way. Okay, so that's showing the direction of the induced current. So there's my induced current, so that is clockwise.
It goes with the way that the current's going in the wire.
Yes, it goes with the induced field. Okay, questions? Yeah?
Is it always gonna be using the two fields to figure out things, or like, are we gonna do examples where we use the current to find the induced field as well?
I think we're always gonna use the induced field to find the induced current, but hypothetically, you could do it the other way.
Yeah, yeah. Okay, cool.
So, that's all about our changing field. Let's ask a different sort of question, same idea. So we start with a big circular wire coil and we squish it. So we make the area smaller. So if we've made the area smaller, have we increased or decreased the magnetic flux? Magnetic flux is B dot A equals B times A times cosine theta. In this case, those thetas are going to be 0 equals B times A. If we squish the loop, we're making the area smaller, right? So what have we done to the flux? Decreased it, totally decreased it. So if we've made the flux smaller, what kind of field do we have to induce to keep it from changing? Okay, are we going to induce a magnetic field into the page or out of the page? So another way to look at these, because sometimes that area bit is a little bit funny, if you look in this circle, 1, 2, 3, 4, 5, 6, kind of got like 6 X's into the page here. That's representative of how strong the field is pointing into the page. If we look at this one, we can see 1, 2, 3 into the page. We don't want it to change, okay? We still want to have 6 crosses into the page. Does that help decide what direction the magnetic field is going to be? Into the page, right? Because we're trying to maintain the original magnetic field. So the induced B into the page. And then your right-hand rule shows the current is coming around clockwise, just like last time. Okay, and that's your right-hand rule. Your fingers are into the page, your thumb is showing the direction of the current in that loop. Yeah, so when in doubt, count the number of X's or the number of dots. Okay, that may help an idea. Okay, one last one, and then hopefully people will have the idea. So in this example, there's a uniform magnetic field. Here's our loop. This is the 3D kind of picture. The magnitude of the magnetic field is increasing. What's the direction of the induced current? So let's start with the magnetic field. What's the direction of the induced magnetic field going to be? Yeah? Down. Anybody agree with down? Yeah, okay. So if it's getting bigger pointing up, to oppose that, we need a field that points down. So our induced magnetic field points down. And then for our right-hand rule, we might imagine that we're grabbing the front of this loop. Our fingers want to go down in front of the loop. Our thumb on the top of the loop is going across this way. So there's our induced current. Yeah?
Would you say it's important to recognize that our induced current arrows are inside the ring? Because if they were outside, it would change the direction of current flow, right?
So we're always talking about the flux through an area. So it's what happens inside that counts. Yeah, it's a good question. So it's the inside stuff that matters. It's always through that closed area. Okay, so let's put this in context of what we opened the last class with. So last class, I brought in the jumping rings. I didn't lug it in again today because it's heavy. So what happened with the rings was we plugged it in, we turned it on, and it made a magnetic field in that coil all of a sudden. So we had that really strong field. there was an aluminum ring around it. The field through the ring changed, so it induced a new field, which induced a current. That current was then sitting in a magnetic field, so it felt a force that made it pop right off. So that was how that worked, right? So it induced a field, which made a current, which felt a force, which made it repel right off the thing. The loop that didn't work, the broken loop, and I think most people were able to notice the difference in the broken one and the not broken. So there's one with a little slit in it. The reason that one wouldn't fly off is because it couldn't make a circuit, right? So it was a broken circuit, current couldn't flow, no current, no force. So that was why that one didn't fly off. This stuff also explains transformers. So this is a very simplified version of a transformer, but functionally it's how it works. So with a transformer, you start with a source of potential, a battery or whatever, and you hook it up to some coils of wire, and typically you would put that around a cord just because you can strengthen the magnetic field that way, just like an electromagnet. So when you hook it up here, as soon as you close the switch, you turn on the current. Turning on the current makes a magnetic field. So it goes from no field to having a field. We have another wire nearby. As soon as we turn this on, create the field here, that field expands and it reaches over to this coil. So what happens is we create a field here, so it creates a field here. This new created field causes a flux through here, which induces a new field, right? So we create a field which induces an opposing field. That induced field induces a current, so it reads current on an ammeter. So you can get current in this one, creates current in this one. That's how a transformer works. The number of coils here, that's how you can increase or decrease the size of that current. So that's kind of more or less how a transformer works. Questions? No? Okay.
So, if that's how a transformer works, how would they short out? Like, if you put too much current in, or if it, like, you know how sometimes when you get a big current, you can short out a transformer? How would that work with that?
I suppose when the current gets too high, you get this big burst. It just burns out the circuit devices that are there, right? You know, you could make this thing catch on fire if the current got too high.
Okay.
So that's kind of where those fires and stuff comes from. Okay, so next, I originally marked this one as homework, but I think maybe it's worth our time to go through in class. So this is the slider question. We did this before with all symbols, but why don't we have another go through it and let's put some numbers on here and see what we can figure out. So I think it's worth our time, even if we do have to give up kind of the fun stuff at the end. Okay, so we take a conducting bar, that's this thing. We know the length of the bar. Call that L. It's on conducting rails, so it makes a circuit. We know the resistance is 0.05 ohms, and we put it in a magnetic field that points into the page, and the magnitude of the field is 0.626 teslas. We're pulling the bar to the right, so there's a pulling force exerted on the bar. And because we pull it, it's moving with a constant speed of 42 centimeters per second. Okay, so that's the situation. Now we're going to ask some standard questions. Find or show the directions of the induced magnetic field, induced current, and induced magnetic force on this sliding bar. So as we take our bar here and we move it over to here, we're going to get an induced magnetic field because we're changing the flux. Is our induced field going to be into the page or out of the page? Okay, first answer, quickest one I got was out of the page. Who agrees? Okay, disagreement? Maybe some not so sures. So as we move it from here to here, we're getting way more X's into the page. We want to oppose that. The way to oppose a field into the page is to create a field out of the page. So out of the page is absolutely correct. So our B induced is out of the page. So that's our dots. We're looking at the tips of arrows. So out of page. All right, for our induced current, let's think about this slider here. We want to use our right hand rule, so we're sticking our thumb out, making a circle with our fingers. We want our fingers to point out of the page, so we're imagining our hand on this part of the circuit here. Fingers are out of the page, our thumb is pointing up, that shows the direction of the induced current is up. And then that's gonna come around the circuit this way, back around here. So there's our induced current. That direction is counterclockwise. All right, so another right-hand rule for our induced magnetic force. Our current is going up, that's I, or L. The existing magnetic field is into the page, so our index finger goes into the page. Your extended middle finger is pointing towards the left, so the induced magnetic field is to the left. Okay, so the right-hand rule, IL cross B gives the force. So let's get that one on the picture. Once you've figured that out from the right-hand rule, you can check it, and you can check it with this right here. It says constant speed, right? So if speed is not changing, if the velocity is not changing, it means the acceleration has to be 0, which means the net force has to be 0. So this force has to be opposite in direction from this force. Okay, so that's just a way to check according to some of the physics things you know. Okay, are we good with all those directions? All right, part B, find the magnitude of the induced potential, induced current, and induced force. We've already dealt with the directions, so now let's find the magnitudes. So let's do induced potential first. The magnitude of the induced potential is going to be the magnitude of d phi dt. Phi stands for our magnetic flux, so that's B times B dotted with the area. B dot A is B times A times cosine of the angle between them. The angle between them is 0 degrees. So cosine of 0 is 1, so we've got d by dt of B times A. The next thing we can do, we want the area of this loop right here. I'm going to call this dimension right here, it's a rectangle. I've already called this the length. I'm going to call this one the width. Calling this dimension W. So the area of my loop is length times width. I can take my constants out front of the derivative. So B is constant, that's not changing. The length of this slider is not constant. This dimension here, however, this is changing because we're pulling the slider to the right, so the W changes. Change in width over change in time, or change in distance over change in time. That sounds a whole lot like speed. So the induced potential is going to have a size of B times L times V. 0.626 Teslas, 0.030 meters, times the speed 0.420 meters per second, gives us an induced potential of 7.89 times 10 to the minus 3 volts, or 7.89 millivolts, whatever. Okay, so that's the size of the potential induced in that loop. Induced current. So we know the potential, we know the resistance, so we can find the current. So that's going to be an Ohm's law calculation. So from Ohm's law, potential is current times resistance. Current is potential divided by resistance. That gives us a current of 0.158 amps. So that's the size of the current. We've already established that it flows counterclockwise. So that was just an Ohm's law calculation. And then for induced force, when we did our right-hand rule, we were saying force was IL cross B, so that's the equation we'll use to find the magnitude of the force. FB equals I times L times B times sine theta. L and B are perpendicular, so theta is 90 degrees. Our current is 0.158 amps. The length was 0.03 meters. B is 0.626 Teslas times sine of 90 degrees equals 2.96 times 10 to the minus 3 newtons. We've already got the direction of that force is to the left. Okay, so that was just F equals ILB. Part C, find the magnitude of the pulling force. We kind of already talked about this a little bit when we talked about the direction of that magnetic force. So for that pulling force, we know it's moving at constant speed because the problem says so. Constant speed means the acceleration equals 0. So in our Newton's second law, the sum of the forces is mass times acceleration is going to be 0. Our net force is the pulling force. That one is to the right. Subtract the magnetic force. Subtract because that one's to the left. Is mass times the acceleration, which is 0. So the size of the pulling force is equal to the size of the magnetic force, 2.96 times 10 to the minus 3 newtons. So that's what happens in these problems. When we move a conductor through a magnetic field, the induced field is always going to oppose that motion and try and keep it at a 0 net force. So that's kind of what happens in all this stuff. Okay. Another example, or skip it because it's boring? Okay, enthusiastic nods for another example. Yeah. Okay, so one person was enthusiastic. I'll do it for one person. Everybody else was not at all. There's not a whole lot of ways to change this stuff up. So instead of pulling something horizontally, let's drop something vertically. So here's something we can change. Looks a little different, but it's still the same problem. So a conducting loop, the mass is 10 grams. The resistance is 2.67 ohms. The width right here is 2 centimeters. The length is 25 centimeters, clearly next scale. It's dropped into a region with a magnetic field of 8.52 Teslas that points out of the page. So this little circle, this is the only place where that magnetic field exists. You might imagine that a person is holding up 2 magnets on either side and it's being dropped in between that area of the 2 magnets. Sort of like when I let the pendulum go and it swung in between the ends of the magnet and we saw that braking force. It reaches a terminal velocity before the top of the loop gets into the field. So while it's dropping, it hits a terminal velocity. Terminal velocity, maybe most people know this term, maybe some people don't. That's a constant velocity. You hear that term a lot around skydivers. They hit a terminal velocity, I think it tends to be like 58 meters per second or something like that. So when you're flying through the air, that's a terminal velocity of a human. So let's think about what happens as this loop falls into the magnetic field. So it starts up here where there's no field. It drops into a loop where the field is pointing out of the page. So it goes from nothing to out of the page. What's the direction of the induced magnetic field going to be? Into the page was the first answer I heard. Agreement? Disagreement? So that's absolutely right. So we go from nothing to out of the page. It prefers to have nothing, so it's going to induce a new field that's into the page to cancel that field that's out of the page. So here's our B induced. Okay, let's ask, what does that mean about the current flow? So let's imagine we're grabbing this little part of the loop. We put our fingers here to show our magnetic field. They're into the page. My thumb is going this way. That's the induced current in that loop. So there's our current induced. And then let's ask, what is the induced magnetic force going to be? So we're always thinking field, current, and force. Those are the 3 things you're going to establish before you even start working on anything. So I cross B I'll go this way. Okay, turn your paper around if you need to. I cross B is out of the page, and the force points towards the top of the loop. Okay, so I cross B is up. So our induced force is going to be up. And that makes sense because we know a magnetic force is going to oppose the motion. The thing is falling down, so we're expecting that force to point up to oppose the falling. All right, so now let's start a Newton's second law analysis. Terminal velocity is constant velocity. Constant velocity tells us that the acceleration is going to be 0. So we can do the sum of the forces in the y direction is mass times acceleration in the y direction, putting our x and our y. So the forces we have in the y direction, this one's actually getting a little bit messy, so let's just draw our loop again over here. We've got the magnetic force that holds it up, and the weight is going to be the force pulling it down, force due to gravity. So our net force is the magnetic force, take away our weight, equals the mass times the acceleration, which is 0, so we'll write that as 0. For our magnetic force, we know that that's I times L times B times the sine of the angle between the current and the magnetic field. That's going to be 90 degrees. Force of gravity, the weight, is M times G. That's going to be equal to 0. Okay, so we're filling in for our forces there. So I times L times B equals M times G. Right here we feel a little bit stuck. We can't do anything about L, that's just a number. Can't do anything about B or M or G, but maybe we could do something about current. That's the only one we can figure something out about, so let's think about current. When I think about current, I think about Ohm's law. Current is potential divided by resistance. If I'm thinking about potential, I'm thinking about Faraday's law. The induced potential is due to the changing magnetic flux, so we can write that bit down. So my induced potential is d phi dt. Phi is b dot A. So it's d by dt of b times A times cosine of the angle between them. That angle is going to be 0, okay, because they're parallel. The area is going to be the length times the width. So d by dt of b times L times W. Constants out front, so we've got b times L times d by dt of W. That's the speed v equals b times L times v. Okay, I did that one a little bit faster, but it was the same process that we did that slider moving to the right. So the flux is b dot A, which is BA cos theta. The area is length times width, and theta is 0. So we put BLW here. B and L can come out front because they're constants. We're left with BL times dW dt, change in position over change in time. That's our velocity. So coming back to our current, potential over resistance, B times L times V over resistance. So we have something we can put in for our current in our force expression right here. So B times L times V times L times B over R equals M times G. B squared L squared V over R equals mg. Solve that for V. V equals M times G times R over B squared L squared. 0.010 kilograms, 9.81 meters per second squared, times 2.67 ohms, divided by 8.52 Tesla squared, and the length squared was 0.250 meters squared. All that in the calculator, and we get 0.0578 meters per second. So almost 6 centimeters per second. It's pretty slow, but oh, I should have brought in the tubes to show you. Okay, any questions? So if you were trying to guess problems for a test, which is kind of a process I recommend you do, like as you're going through the examples in the class notes, what could I ask that looks like this but is a little different? We just did falling into the loop. How about falling out of the loop? That could be like a decent question. So you might want to think about stuff like that as you're getting ready for the exam. Any questions here? No. Okay. So one last application, and this is just going to be qualitative. We're not going to do any numbers here. There's loads of differential equations you can solve, and we're not going to do any of them. So when we talked about circuit devices, we talked about resistors and capacitors. The other circuit device that you'll see mostly is called an inductor. So an inductor is a little coil of wire. Imagine a slinky, only it's a lot smaller. So it's a little coil of wire, and what we do with an inductor is we put it in a circuit and we hook it up to a battery. When we hook it up to a battery, we get a current through the wire, and it makes a magnetic field. Okay, so that's what an inductor does. It's a little coil, put a current through it, we get a field through it. So then we apply what we know about Faraday's law. If we change this current, for example, if you have an AC current supply that flips back and forth, if you change this current, you change this B, which induces a new field and a new current and a new potential. Okay, so changing the current through an inductor will induce new fields and new currents. And then what we do with those circuits, I'm not going to give you any diagrams like this on the test. You won't see this coming up. But what happens is you put them in circuits with capacitors, or with capacitors and resistors. When the capacitor discharges, right, it lets off charge, charge moves, makes a current, that current changes as it goes around. Changing current makes a changing field, which induces a new current. Those things get currents moving back and forth in circuits. So that's kind of what happens as a capacitor discharges. Changes the current through here, induces a new current, which will charge the capacitor back up over time. That's the sort of thing we're going to look at quite a bit in Physics 2055. So if you do that, you'll see it again there. Or if you go on to electrical engineering, you would do a fair bit there. If you never go on to any of those things, you can kind of forget those last two slides ever existed. It won't impact you very much. So I guess that's a good place to quit, unless like people have a burning desire to see how electric and magnetic fields are the same thing.
Yes.
Yes? Oh, okay. All right. I figured everybody would just want to like run. Okay. So, and I'm not putting this as a question on the test either. I just think this is cool, which is why I put this on in the course. So we're just going to talk about it conceptually, like a few equations just to give some context. So let's set up the situation. And first, let's just kind of come back to Faraday's law for a second. We said Faraday's law was induced potential is the change in flux with change in time. So if we change the flux, if we change a magnetic field, we get an induced field, an induced current, and induced potential. If we have current and potential, where do those things come from? They come from electric fields, right? So changing a magnetic field does something about the electric field. Those two things are clearly linked, right? So your induced potential epsilon, potential goes with electric fields, but magnetic flux goes with magnetic field. There's a tie between those two things. So here's our thought experiment. We've got Alec and Brittany, and they're out, I guess they're doing some experiments. Alec holds up two giant magnets, and it makes a magnetic field that points in this direction. Okay, so he's got his giant magnets. Alec knows there's a magnetic field there because he's making them with magnets. Brittany is standing up. She's going for a run, and in her hand, she's holding a positive charge. Okay, so that's her situation. She's got that on a little golf tee or something. She's holding a positive charge. So now let's ask, what does Alec see? And what does Brittany see? What does it look like to each of them from their own points of view? Okay, and remember, Alec is making the magnetic field. So, Alec is making the magnetic field. Here's what we just said. Brittany is holding her charge Q. She's running with some constant velocity V. So that charge is moving through a magnetic field. That's what Alec sees, right? So Alec is looking at Brittany. He sees her moving. She's holding the charge, so he sees a moving charge. So according to Alec, Q is moving. If he sees a moving charge, then it has to have a magnetic force, which is equal to Q times V cross B. That's what we've been talking about for like a whole chapter. Magnetic force is QVB. But what does Brittany see? So she's running, the charge is in her hand. According to her, that charge is not moving, right? So this water bottle is not moving relative to me. It is to you, but not to me. So to Brittany, the charge is not moving, so she doesn't see a magnetic force at all, right? Because the charge is not moving. We only get magnetic force when the charge moves. So according to Brittany, the charge is still FB equals 0. So who's right? Because they each have an argument to make, and from their own point of view, they each think they're right, but somebody has to be right. So we know that force is mass times acceleration, and we should be able to agree on accelerating. Either something's accelerating or it's not. And if we agree on acceleration, we should be able to agree on force. So why do they disagree on force? Okay, and the answer is with V. Remember in Physics 1020 and 1050, probably the most hated part of the entire course was the relative velocity problems. Getting some nods, right? So when we talked about velocity, we never once said relative to what. Turns out relative to what is an important question. Okay, so we've got to think about relative velocities. So let's put on some coordinate systems. Alec, Brittany, and ground. So Alec is like the ground. He's standing still. Alec is not moving. If he's not moving, he's certainly not accelerating, so his acceleration is 0. B is the red one. B is for Brittany. She's running with constant acceleration or constant velocity, so her acceleration is 0. The acceleration of Brittany is 0. We're going to call C our charge. This charge is definitely moving. And these two, or let's say our charge is moving, these two can each describe the charge's motion relative to themselves. So Alec would see it moving, velocity of charge relative to Alec, and Brittany would see it, velocity of charge relative to Brittany. Okay, so they would each see the velocity of the charge relative to themselves. So let's do our relative velocity equation. So Alec is like the ground, charge is the thing that's moving, and Brittany is the thing that it's moving with respect to. So the velocity of the charge relative to ground, or relative to Alec, is the velocity of the charge relative to Brittany, plus the velocity of Brittany relative to ground, or relative to Alec. So Brittany moves relative to ground, relative to Alec. So this is Brittany's motion. That's the charge relative to Brittany. Add them together, you get the charge relative to Alec. So now we've got a relationship between those velocities, and nothing is accelerating here. Everything's constant velocity. That bit's pretty important. If the velocities were changing, right, remember we said one person saw force and one person didn't, so one person's saying there is an acceleration and one person is saying there's not. So let's think about how we would find the acceleration. So the acceleration of the charge, you do the derivative of the velocity. So the derivative of the velocity of the charge relative to Alec with respect to time is the derivative of the velocity of the charge with respect to Brittany with respect to time, plus the derivative of the velocity Brittany relative to Alec with respect to time. Okay, so we would do the derivative of that equation to get the accelerations. So the acceleration of the charge relative to Alec is the derivative of the charge relative to Brittany. Acceleration charge to Brittany, plus the derivative of Brittany relative to Alec, but she had constant velocity, so that's 0. So this equation tells us that they do agree on the acceleration, right? So the charge relative to Alec has the same acceleration as the charge relative to Brittany. They agree on acceleration. So if they agree on acceleration, then they have to agree on force, because force is mass times acceleration, but they didn't agree on force. Okay, why not? So let's go back to our picture. And let's remember that Alex saw a magnetic force on the charge. So this force, according to Alex's description, is a magnetic force. And he could get that force by the right-hand rule. And Alex saw the force, FB equals Q, velocity of the charge relative to Alex, crossed with the magnetic field that was made by Alex. So I put an A on this because he made it. So Alex saw the charge moving in the magnetic field that he made, so he saw the force, and he's calling it a magnetic force because there was a field and the charge is moving in the field, okay? So Alex is saying, I agree with what we did in class for the last month. This is the force we saw. Well, what about Brittany's point of view? So we concluded that Alex and Brittany had to agree on acceleration, right? So we thought about the relative velocity. We said that they agreed on the acceleration. So Brittany is going to say, I agree this charge has an acceleration. I agree that the force points up, but it's not a magnetic force because that charge is not moving in a magnetic field, right? Because relative to her, the charge is not moving. So it can't be a magnetic force. What else makes a force on charges? That's electric field. So Brittany has the charge in her hand. She agrees there's a force. She doesn't agree it's a magnetic force, so she says it's an electric force. Because an electric field is what can make a force that points up if she's not moving in a magnetic field. So according to Brittany, there is a field, but that field is an electric field. Because she says it has to be an electric force, because she says the charge is not moving relative to her, right? To her, that charge is still. So now Brittany sees the electric force, Q times E, and we're back to the question, who was right? So Alex says it's a magnetic force. Brittany says it's an electric force. The answer is they're both right. Okay? We don't have one right and one wrong. They're both absolutely correct. So whether it's a magnetic force or a magnetic field or an electric field depends entirely on your point of view. Okay? So those two fields are really the same thing, but you get a different description depending on your own relative motion. So electric and magnetic fields are kind of the same thing. So this was a Brittany's force, this was Alex's force. Velocity of the charge relative to Alex, so it's the velocity of Brittany relative to Alex, because she's holding the charge. So Brittany's force, QE cross B, was equal to Alex's force, QV, Brittany to Alex, cross the field made by Alex. Your charges cancel, so the electric field that Brittany sees is her velocity crossed with the magnetic field. Okay, so what you see depends on your point of view entirely, okay, so your motion. So I think that's pretty nifty, and we'll do more of that in Physics 2055 too if you're interested. If you like that kind of stuff, you might like Physics 2700, like the modern physics. That does a lot of cool stuff too. So anyway, we really will quit there, 5 minutes to spare. So thank you. It's been a good semester from my point of view, and I hope it was kind of good enough from your point of view.